So we briefly talked about thermodynamics in Chapter 5 of the textbook. And the descriptions that we looked at in Chapter 5 deal with enthalpy. When we look at the overall scheme of thermodynamics, we need to consider enthalpy and entropy. And collectively, those two terms go together to figure out something called a Gibbs free energy. So that's where we'll be working up to. But before we jump into this free energy stuff, let's kind of go into some of the background and introduce a couple new terms. So thermodynamics is our next unit that we're going to spend a decent amount of time on. And like I said, it's chapter 19 of your textbook. With these thermodynamic quantities, we make some observations and stuff like that in the lab, and then we come up with various laws. There are three main laws of thermodynamics. They start with a more general description and then get a little bit more specific as you go on. So the first law of thermodynamics is often referred to as the law of conservation of energy. And basically, what this energy conservation law says is that energy cannot be created or destroyed, but it can be interchanged from one form to another. So the question is, how do we take this statement, which I'm sure we've all heard before, and make this relate to what we're doing in chemistry? Typically, we see various chemical reactions, and we tell you to be able to identify what these reactions are. There's something called a combustion reaction, and in that combustion reaction, you typically have a hydrocarbon plus oxygen, giving you CO2 and water. And we can write out a generic form of that reaction by saying we have CH4 plus 2O2, which are reactants, giving us CO2 plus 2H2O as our product. Most of these combustion reactions are exothermic reactions, and they're going to be able to produce a lot of energy for us. That energy is often given off as heat. So what the law of conservation of energy is telling us is we can't create or destroy energy, but it will change forms. So what this tells us is that if I have reactants going to products giving off heat, that heat's a form of energy. So this has to tell us that something's going on with the energy on the left-hand side of the equation and the right-hand side of the equation. Because this heat wouldn't be given off if it was just created out of thin air. We have to interchange the energies. So the energies of the left-hand side of the reaction and the right-hand side of the reaction are going to be different. So to visualize this, and what you should be thinking about when you see a balanced chemical reaction, is think about it in terms of all the molecules that are present. So we're going to have CH4 as a tetrahedron with a carbon and 4 hydrogen bonds. Then we're going to have 2O2. So we're going to have plus 2 of these O2 molecules is going to give us CO2, which is a carbon double bonded to an oxygen, double bonded to another oxygen in a linear fashion, plus 2 waters. So here are all the molecules present in this particular reaction, and we know that heat is given off right here. We can estimate these reactions by saying, looking at the bonds broken versus the bonds formed. So if you can try to remember visualizing those little molecular model kits that you used in the last experiment of Chemistry 121, you can put the atoms together, and you can rip them apart, and you can assemble them in another way. And so you're assembling and putting together all these atoms and molecules, and it takes energy to break a bond. And when a bond's formed, it's going to lower in energy. So we can compare energies of bonds broken versus bonds formed. So in order to go from CH4 plus two O2s over to these products, we need to break bonds to do that. So the bonds that we're going to break are, in this case, we have a tetrahedron. And it has 4 carbon-hydrogen bonds. So we need to break 4 of them. We also need to break 2 oxygen-oxygen double bonds. So here's our total of our bonds that are broken. Bonds that are formed are going to be our carbon-oxygen bond times 2. And in each water molecule that's formed, we have an oxygen-hydrogen bond forming. There's 2 per molecule. We have 2 molecules. So this is going to be times 4. And when we go from breaking these bonds to forming these bonds, there's going to be differences in energy, as indicated by the heat that's given off in this particular reaction. So the question is, can we take this particular reaction that we're combusting, and can we put that energy to good use? The thing that really sucks about these energy applications, and we have this energy crisis that we're dealing with, if we could make efficient ways to convert these energies, we would be set. Have no problem. I think I was reading last night when I was preparing for this lecture that for every 100 watts that powers a 100-watt light bulb, we get 5 of those watts back in light energy. The other 95 are quote-unquote wasted to heat. When you have a combustion reaction, the most common combustion reaction that goes on in our lives is gasoline being combusted to power our cars and our vehicles all over the place. The efficiency of those is just minuscule, and we lose a lot to heat as evidence of how hot your engine's going to get. So we can monitor how this heat transforms and how everything goes around. But what we can say about this reaction to tie the first law of thermodynamics, this law of conservation of energy, into these molecular reactions is that in this exothermic reaction, when we progress from reactants to products, there is a lowering in potential energy stored in the chemical bonds. And basically, what we're seeing in this case is we have potential energy being converted to thermal energy. So each of these bonds, this chemical bond, has a lot of potential energy there. And it's a great way to store the energy. You've heard about hydrogen fuel cells and a hydrogen economy. That hydrogen-hydrogen bond has a lot of energy stored in that chemical bond that we can put to good use. And it stores it in a very, very small way. And a lot of your plants, they choose to store their energy in the chemical bond because it's the most efficient and it's a very compact way to store all the energy that they need. So we have a lot of potential energy that's stored in these chemical bonds. And this is how I like to think about the first law of thermodynamics, or the law of conservation of energy. The law of conservation of energy, though, kind of is like a hand-waving way of saying, hey, energy can't be created or destroyed. It's going to be transferred in different forms. But the first law provides the means for accounting for energy, but it gives no hint as to why a particular process occurs in a given direction.